Hello, I'm Zhang Yabin from the Hong Kong Polytechnic University, and I'm going to present our CVPR 2022 paper, Exact Feature Distribution Matching for Arbitrary Cell Transfer and Domain Generalization. Distribution matching is a long-standing statistical learning problem, and many practical tasks can be cased as a specific case of it. For example, in cell transfer, image cells can be interpreted as feature distributions, and the cell transfer can be achieved by cross-distribution feature matching. Existing methods typically align feature distributions by matching the first and second order statistics. Arguably, the most popular method is to match the mean and standard deviation. This is based on the assumption that the underlying feature distributions follow Gaussian. However, the practical feature distribution is far from the Gaussian. Thus, aligning the mean and standard deviation may only match feature distributions roughly. Taking it a step further, we observe that different cells have different higher-order statistics, suggesting that image cells can also be represented by higher-order statistics. Therefore, could we perform better cell transfer by conducting feature distribution matching more exactly? The most direct way for exact feature distribution matching is to explicitly align higher-order statistics. However, it is computationally expensive to operate on those high-order ones. What's more, the exact matching is only theoretically achieved when the considered order approximates infinity. So what about aligning higher-order statistics implicitly? Histogram matching is a popular method for distribution matching. However, it only achieves distribution approximation instead of exact matching, as presented in the following slides. Here we compare ADA-IN, histogram matching, and our proposed EFDM on a toy example. Only our method achieves exact matching of various order of feature statistics. Similar to histogram matching, we aim to exactly match distributions by exactly matching the empirical cumulative distribution function. Specifically, give input vector x and target cell vector y. We first sort the values respectively in an ascending order. To obtain the required output, we replace the sorted x with the corresponding position of sorted y, and then return the unsorted x, whose elements are replaced with y values. In this way, the output O will share identical feature distribution to y. Usually, the gradient to x is required. Thus, we modify the linear equation slightly. Finally, the proposed EFDM could be achieved with a few lines of code in PyTorch. We follow the ADA-IN to conduct cell transfer. Specifically, we replace the ADA-IN module with the EFDM module for more exact feature distribution matching, and we update the cell laws to measure distribution divergence more precisely. Qualitative and quantitative results justify the effectiveness of our proposed method. In domain generalization tasks, we aim to transfer knowledge from seen domain to unseen domains. A typical solution is to generate cell transferred images or features as additional training data. To facilitate the application of EFDM to domain generalization, we first introduce EFDM mix to produce intermediate domains via interpolation. Results on domain generalization justify the effectiveness of our proposed method. Here we analyze the role of different order of feature statistics by matching higher-order components. More content details are preserved in cell transfer, while better results are achieved in domain generalization. Although the time complexity of EFDM is O(n) log n, the practical runtime is comparable to ADA-IN, since the feature dimension is really limited. That's all. Thanks for your time.